Okay, so we're gonna walk through some functions on principal component analysis. Um, so in Mathematica, you can do singular value decomposition, which is similar, the same thing as principal component analysis. Anyways, I'll walk you through a bit. U sigma v equals sigma. So let's say we have a data 1, 1, 2, 2, 3, 3, 4, 4. So you can just do one line through it. So to get back this data, you do u dot sigma dot transpose v, and you get u sigma v by running this function in Mathematica. And you get back 1, 1, 2, 2, 3, 3, 4, 4 to 2, same as the original data. So to get x approximate, since we don't need all the columns of u, we only need one column of u because we can clearly see there's only one principal component. We just use the first column of u, and first we have to truncate sigma to the first value as well. So u dot sigma dot transpose v gives back our original 1, 1, 2, 2, 3, 3, 4, 4 because there's only one principal component. So using one principal component gives our exact function back. But if there were two components, the approximate original would be not the same. So let's say our data now is 1, 1, 2, 2, 3, 3, 5, 4. So you can't, let's say there's some noise and it's a 5, 4, but you still get a main principal component with a bit of noise as a second principal component. So when you just use the first principal component, you do u dot sigma dot transpose v with sigma only. You have to make this. You only use the first non-zero value of sigma and the first column of u, and then you get approximately the same as original data. So this is original data, and then this is the what you get back. So like 1 0 1 1 and 2 1.86 2 2. So they're similar but not exact because you need second principal component to get the noise back or whatever it is that caused this to be 5 instead of 4. Since principal component analysis subtracts the mean by default, doing principal component analysis on original data and on mean center data results in identical principal components. So let's say PCO equals principal components of data, and then we get this principal components. Then if we do find the averages of data and subtract those averages from the data, we get seed data. And then if we do PCC equals principal components of seed data, then it's the same thing. So PCC equals PCO, meaning that if we do principal components on center data, it's the same as principal components on the original data. To get principal components using SVD, first center the data, then do u dot sigma. They're usually a -1 inversion somewhere, so signs may not be the same. So u sigma v again equals singular value decomposition of centered data. U dot sigma is that, and then that is the same as doing principal components of seed data, except that there's a minus sign somewhere. Principal components function returns first principal component as the first column. So if you get confused, like which one is first principal component, is it like which direction? Anyways, so you just do PC equals principal components of the data, and you get this in return. And first principal component is the first column. So PC1 is PC and not of the first column. So this is the first principal component. And then principal component 2 is zeros, but that's if we use this one. So let's rerun it. So yeah, again, there is no second principal component because it's 1, 1, 2, 2, 3, 3, 4, 4. So you only need one principal component, and there you go. To map the new point onto the new plane, i.e. to figure out principal components of the new point, uh, you do xn dot v, where xn is the new point. So if we use the old point, we get the original principal components of that point. So let's say our data is 1, 1, 2, 2, 3, 3, 5, 5. We do averages, we center the data, we do single value decomposition, and so here's we check the new point, which we just use as an old point. So our old point is seed data, the first point of the seed data. We do dot v, and then this is the first and second principal components, uh, if we of that first point. So that's 2.47 is the first principal component value, and that's the same as if we do the principal component uh, function, and we can see that it's the same 2.47, and then we can do the second data point. We'll map it back into principal components, seed data 2.v, and then we get a first principal component of that point is 1.06, which is the same as what we get as for it using principal components analysis. And then if we get completely new data, it clearly that's what we are interested in, is mapping the new point onto the old plane and to the old principal components. So let's say our new point is 1.1 and 1.1, and we dot that with v, and then we get this would be the first principal component of that new point, 1 point minus 1.55. And this minus here that keeps coming up is just you never know what you get back as far as principal components. Sometimes you have to multiply by -1 because the computer doesn't know up from down, left to right, and it sometimes inverts them. So, yeah.